Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Hannah Susorney with us today. Hey, Hannah.
Hi.
How are you today?
I'm doing good. I'm here in rainy England. And
okay. I'm here in Phoenix, Arizona. And so how has the summer been in northern latitudes there?
it's actually, we've had a very cold one. I had all my summer dress, and I was just complaining to my dad today that I haven't been able to wear all my summer dresses, and summer is over. But I've heard in the US you've been baked alive, so.
Particularly in the West, there's still many fires going on. None here in Phoenix, but definitely other parts of the West are burning. Yeah. On the other hand, maybe with the end of summer, you've got the Northern Lights coming up. Do you see the Northern Lights where you are?
No, we actually don't. I think it's probably about too overcast. I have now moved to a more rural area, and I did the classic like everyone else did. I moved during the pandemic, but I think you might need to go up to Scotland. So I'm down and I actually live in Dartmoor in southern England now. So
very cool, very nice. Let's see, Hannah, what do you like to do for research?
So I'm really interested in the surfaces of rocky planets, and really my research is kind of composed of two things. So Mercury, what I'll be talking to you about today, and actually what I've primarily been funded in, this is Mercury kind of a little side project, is studying the surfaces of asteroids. So I've been involved in quite a few missions. Messenger, which is the data set we're going to talk about here, was primarily doing my PhD, and then I was on OSIRIS-REx, and I've been working with a lot of asteroid data sets.
Very cool, very cool, very cool. Yeah, we have a little people involved in Messenger here at Arizona State. So yeah, so let's take a look at this really lovely PSJ article. Morphometry and temperature of simple craters in Mercury's northern hemisphere, implications for stability of water ice. And Hannah, take us away.
Okay, so this paper actually has quite a nice story because it kind of started at the beginning of my career, and I read it quite recently. So a lot of this data is all from the Messenger mission, and I was actually, when I was an undergrad, when I did my first year in planetary science, I was an intern on the Messenger mission, and this was actually part of my intern project that had never gone around being published. And then finally, I ran into my co-authors, Carolyn and Nancy. At a conference, we got chatting, and I was like, whatever happened to all that work I did? And they're like, oh, a couple other interns, Ariel, one of the other co-authors, and then Evangelina, who's mentioned in the acknowledgement, they added more to the data set, and they're like, why don't you write it up? So it was quite fun. I got to actually dig through a bunch of data files I made when I not 10 years ago, but back when I was first learning how to make data files. So it was a bit like, oh God, what did I do? But it was actually a really fun project to do, to see how I've both changed as a scientist, because all the data, all the analysis was done ages ago. So it's really just putting the paper together. Very cool. And it's just kind of a fun blast of the past with my PhD supervisor is the final co-author. So it was all these people that were with me at the beginning of my career. Oh, and awesome. Now I'm, kind of gone elsewhere and started doing other things.
So to those undergraduates who may be watching, or early grad students, sometimes these side projects that you do or internships can blossom.
Yeah.
Years later.
Years later, I'm like, oh, we finally finished that.
Yeah. Very nice. Very nice.
So yeah, so it's kind of the idea of the project. So the project is really kind of comes out of one of the major parts of the Messenger mission, which was looking at the polar ice deposits on Mercury. And if you're not really super up to date with planetary science, you might not realize that closest planet to the sun actually has water ice on the surface, or what we're pretty sure is water ice. And this was one of the main drivers for the Messenger mission. So we knew there was something weird at Mercury's poles since the 1990s. So back then, the Arecibo Observatory in Puerto Rico, which is sadly no more, looked at Mercury's northern pole, or north and south pole, and saw that there's this high reflective region. And there's several different explanations, but the one they kind of came up with that seemed to make the most sense was you're actually looking at water ice. And the question is, like, how do you have water ice on the closest planet to the sun? And the simple thing is Mercury doesn't wobble. So we wobble, the Earth wobbles around. So, anything that stays at the very top, you're going to see it. Mercury, the North Pole does not see the sun. And there's topography there. If it was a smooth sphere, there would just be a single point that doesn't see the sun. but there's impact craters because Mercury's been out there. It's been blasted by lots of other asteroids. So you have topography. And then, so when the sun's coming in at the poles, there's regions that never see daylight, no matter at all. They're in permanent darkness. And this is with, a bunch of other lines of evidence from the MESSENGER mission. We're fairly confident that this is in fact water ice. Now, okay, so we have water ice in Mercury, but there's a lot of questions. So like, how long has the water ice been there? Is it stable? Where's the water ice from? Like, how do you get water ice into the inner solar system? And one of the main things trying to, back this up is we need more information about the ice. So one of the things is the water ice stable? So can it exist in these cold traps for like billions of years, or is it a million of year phenomena? So there's a lot of modeling done going into the MESSENGER mission. So there's lots of people who have expertise that are different than mine who can do these thermal models. And one of the things they came out was saying that the water ice should not be stable in small craters.
Okay.
And that was one of these huge things, like we should not, if we see water ice in tiny craters, it means the water is young. Right. Well, we get there, we get really good data sets, we get the imaging of the poles, and then we actually get better radar observations kind of going up into the MESSENGER mission. Right before we got there, we got really good radar observation, and we see water ice in these cold traps. But we're all geologists, and geologists just think like, oh, geologically young, like things tend to be stable. What's the chance of us happening upon Mercury after it just randomly got all its water ice? Okay. So we kind of tried, the idea of this is to kind of revisit this idea. Is this water ice stable? Because the other interesting thing about these papers that have been modeling the stability of water ice, they use kind of an idealized impact crater ratio. So they said that the impact crater should be 20% of the diameter, which is kind of the standard ratio. But they had this interesting side note saying that, well, if we did some other modeling of different impact crater depth diameter, if they're shallower, they're actually more stable. The walls are less steep and you're bouncing less light down because the walls have a lower angle. So you're bouncing more light out. Yeah. So it's kind of like, maybe we should look at these little craters. And so the main point of this study is actually looking at this depth diameter relationship. So is it 20%? Is the depth 20% of the diameter? And then also working off of the fact that there have been temperature thermal maps made using updated Mercury topography. And what is the model temperature in there? And how does that match with these previous studies? And what does that say about the stability of these small craters that have radar bright deposits? I keep calling it radar bright, and that's really kind of where we're looking. We see the water ice. It's the high radar reflectivity. So if I mix up saying radar bright and water ice, I'm referring to the same things in my brain. They're just jumbled. But if we want to go down to figure 1, you can kind of really see what I've been talking about these polar deposits.
Let's do a little blow up there on Mercury.
Oh, yes.
There we go.
So this is a polar view of Mercury's North Pole, and I'm talking just about Mercury's North Pole, and that's because of how the MESSENGER mission was the mission design. So Mercury, okay, I'm talking about water ice, but the surface is actually quite hot. And if we leave a spacecraft close to the surface, it's going to get burnt, which is bad. You don't want to burn your spacecrafts. So we kind of do these close passes of the northern pole and then go cool off in space and come in again. And just with the design of the mission, we're really limited to good quality data at the North Pole. So this is an image mosaic. So it's black and white kind of image mosaic of the North Pole from 75 to 85 degrees north. So really just kind of this tight polar region. Mm-hmm. And what we're showing on top of the images are craters, all the craters between 5 and 10 kilometers in diameter. Okay. And I'm talking about these are small craters, but remember Meteor Crater in Arizona is 1 kilometer in diameter. So the smallest ones are 5 times Meteor Crater. So there's 2 different there's the colors on here is craters. The green craters are craters that do not host radar bright deposits, and the pink craters are craters that host radar bright deposits. And this was just kind of our first level work we did. So we wanted to look at these depth diameter relationships. Let's first figure out what craters actually have the radar bright deposits, which ones we're talking about. So this is really just the data set we're working from. And you can see some interesting trends here. I'll talk about the paper. While the paper itself focuses on this depth diameter relationship, we did just kind of want to look at this crater population overall. You can see there's a lot of craters that host radar bright deposits in some areas. There's less so in others. And I'll talk about that a bit more later. Yep. But so if we want to go to figure 2, I know it goes buzzes out of it. Okay. It's a similar figure, but the craters are just identified a little bit different.
Okay. Okay.
So we have, so I was talking about this depth diameter relationship, and that's what we need topography data for. So that's kind of my expertise, is kind of in topographic measurements of various planetary bodies. So here, really, there's lots of different craters identified with different circles, but they're the same craters as before, and I'll just kind of walk you through it.
Okay.
So the white craters are the craters we didn't measure the topography at all at the topography at all. And the main reason was usually that the topography around it was quite degraded. It's difficult to measure. Let's focus on the better craters. I mentioned before, there's two different topographic data sets we're using here. So one of them we're using our individual MLA tracts. So that's the Mercury laser altimeter. And that was the main altimeter. So it just pretty much bounced a laser off the surface. As it flew over the surface, you measure the time from when you sent the laser down to the laser comes back. You then, you know where the spacecraft is in space. You get the topography coming out. The gridded data set is the prettier data. It's when you've taken all those MLA tracts and you made a beautiful gridded data set.
Yes.
Beautiful, but it has errors in it. So one of the other things we did in this study was we used both data sets and we measured the same crater multiple times. So you can see here, red craters were measured with the gridded data set alone. And that's usually because there wasn't actually the best MLA data around it.
Okay.
So, and then the blue craters were craters that were just measured by the MLA tracts. But the interesting thing are the pink craters, because they were measured both by the gridded topography and the MLA data. So we're actually able to compare these two data sets and see if they differ and see if we could actually use both data sets in the same study, because we had more faith in the MLA track data than in the gridded data. But I think figure 3 might be the kind of the interesting thing with this one. We'll see. No, I think I might have you bump slightly. I think it might be figure 5. Sorry to have you drive around.
Okay. I like driving. Figure 5.
Yeah, it was like, now I'm talking about it. It's very so talk about the different types. So figure 5 is plotting the difference in depth diameter for those pink craters. I said they were measured by both data types and showing that what their difference in depth diameter actually was. So you know, if I measured it with MLA only versus gridded only, and the thing we can see here is, okay, there's a bit of scatter, but the main thing is, so we're interested in depth diameter measurement. The overall one that the study had done before, that the previous study about Mercury small craters used the depth diameter measurement of 0.2. And here we're seeing differences in the 0.04, 0.02, possibly slightly biased, but we're just kind of, you know, there's just going to be noise in the data set. So we actually looked at this and went, you know what, it's not a big tail in one direction.
Right.
It's okay-ish. Like, you know, what I always say when I measure, I spend a lot of my life measuring craters, is I would never trust a single crater measurement. Okay. But you measure 200 of them, it'll work itself out. So it's pretty much just saying that, like, they're comparable data sets. Sometimes the gridded one's bigger, sometimes the MLA track is bigger. You know, it's the data, you know, the spacecraft was, you know, a couple hundred kilometers above the surface. You can only ask so much out of it.
Yeah.
I'm happy, you know, it's okay. So what I think zoom back, if it's okay to zoom back out, so I can try to remember where all the other figures are, because in my head they are all, so I think we'll just skip 3 or we can just do a quick aside back up to 3 and 4.
3 and 4 are geolocations and percent.
Yeah, this is kind of what I was talking about. So if we just don't think about the crater measurements for a second, just think about where the craters are. Right. We see this is the percentage of the craters that are radar bright, that we can see water ice. And for if you look at figure 4, the lower one first, we can see that there's just a general increased latitude. That makes sense. If you're further closer to the pole, you should be, more craters have the ability to hold radar bright. There is this very strange longitudinal variation, and I'll talk about it a bit more later. Okay. Like, spoiler alert, we still don't really know. Okay. So it's interesting that, like, all the interesting explanations we kept going, like, oh, maybe, oh, I'm not sure. So I think it's one of these things that we can kind of talk about at the end about kind of where to go with this in the future. But you know, it's that whole thing, you know, you do a study and it gives you more questions and answers. Very good. Yeah. So, but pretty much just showing kind of a different way of looking at the distribution. But if we want to pop out to create, it's figure 6 to show some of the exciting results.
Figure 6. There we go. Let's blow that up. Okay, yeah, there we go. Diameter depth.
Okay.
There we go.
I know it doesn't look like the most exciting plot in the world, but it is. So I mentioned before there's this important 0.2 ratio depth diameter, and that's what was used in these modeling studies and saying that if you see radar bright stuff in craters under 10 kilometers, the ice is likely to be geologically recent. Well, almost all the craters we measured were shallower.
Okay.
So what this is really showing is that most craters on Mercury are not this idealized ratio. And when you think about the idealized ratio comes from this idea, you know, it comes from modeling in an experiment where you make a crater and measure it instantly. But the craters we're all looking at are millions to billions of years old. They've been getting smushed by other things. They've been getting eroded. They have landslides. They have other craters inside it. The rims collapse. The craters will just naturally shallow over time. And also just, you know, there's just this natural variation. You know, you see some craters here are deeper than that 0.2 ratio. Most of them are in fact shallower. So there is this, I guess the biggest thing that can come out of this is there is no ideal ratio. And even this is kind of aside from this study, but looking at this, there isn't one perfect ratio. The craters don't all plot on a single line for any other ratio. They are natural features and have natural variation. And there are large error bars on here. So the way we measured it is we measured it in several different orientations and directions across the crater. So sometimes the rim is higher on one side, it's shallower on the other. So it's kind of like, you know, the crater is in the middle and we kind of bisect it in different ways. So there's just variations in the crater from the way you're looking at the crater. So it's really just showing that even the diameter, how do you measure the diameter of the crater? Diameter might be different in different orientations. So there are error bars on these measurements, but the main thing coming out of this is that the craters are shallower than previously estimated. And the big take home point is that, and we'll talk a bit more about the thermal results, is that means that this water ice is not restricted to be geologically young. It could be any age. It could be here. It could have been put back billions of years ago, or it could have came yesterday. We don't know. And what that means is going forward is you can't use it as a constraint, and then you have to actually revisit a lot of those models. And so that's something that's been done to a smaller extent with actually modeling the temperatures of the actual topography, but that hasn't been done in the detailed modeling of individual craters. And so that's what's really saying is that we need to realize that craters, this 0.2 depth diameter ratio isn't really true. So you need to measure these larger range, because craters aren't perfect. They're not. You know, Mercury is a laboratory where you get perfect results every single time. So that's kind of the big picture thing. But there's some more because the study took so long to get going. When I was first working on it, there weren't temperature maps for the surface. So this would have been end of story paper, even shorter. But the really exciting things was between when I did this work in, I think it would have been 2011 or 2012. And when we kind of got together and wrote it up in 2020, that there actually had been work done on the temperature results. So I think in figure 7, if I actually remember them correctly. See, figure 7 trying to be something completely different, and I'm talking nonsense.
There we go. Okay.
Oh yes, it is actually something completely different. But
you want to slide
why don't we skip figure 7 and we can come back to, I think, figure 8, which is the panel. Come back to it.
Yes. Temperatures. Yep.
Yeah. So I was talking about there's been exciting work done since then. So again, this doesn't look like exciting work, but it is exciting work. So what this is so part at the end of the messenger mission, we got these topography maps, and people who did thermal modeling modeled them. So Page et al. And it was also the more updated maps with put in Nancy Chabot's chapter in the Mercury textbook, actually had gridded temperature maps of the entire surface.
Nice.
Which is awesome. Well, we know where all these craters are. Why don't we go look at what the model temperature is in there? So the things with all these plots is, so they kind of show, so A and B is the maximum temperature. So that's in Mercury's thermal years, 2 years. So what is the maximum temperature that pixel, or the pixels within that crater, or within specifically the radar bright or shadowed region of that crater field? What is the maximum temperature of any of those pixels? Or no, that's maximum temperature maximum temperature of any of those pixels, sorry. And then the same, what is the average temperature throughout the year of any? And so what that is showing, so that's telling us a different story. So the maximum temperature is saying is water ice stable on the surface? Because if it ever exceeds that maximum temperature, you're going to evaporate that water ice. And the temperature we care about is at 110, which is that dotted line. So actually what it's saying is, okay, it's all too hot.
Okay.
But the interesting thing is if we look at C and D,
okay,
but is it too hot underneath some rubble on the surface? And that's what average temperature is telling us. It's telling us if you have an insulating, we call a lag deposit, it's really just some rocks or other debris on the surface. Is it actually cold enough underneath them? And the answer is yes.
Okay.
So it doesn't match one for one. So here, you know, the non-radar bright craters are black and the radar bright craters are blue. And that didn't bother any of us because simply put, these all the data is quite messy. So the topography maps have quite low resolution because the grid topography has quite low resolution. So it's not going to capture all the little pockets of water ice that might have been picked up by radar. Some of the ice could be geologically young. So there's lots of different things that could be impacting individual data points on here. But the general picture is it is actually cold enough underneath these lags. So, and this actually really does match a lot of the other observations. So one of the really cool things one of my co-authors here, Nancy, has done is she was one of the main scientists on the camera. And she, with the engineers, what they did is they left the camera open. They didn't have a really quick shutter, so it allowed extra light in. They oversaturated the images when they were imaging these permanently dark regions. And there was enough reflected light coming in that they could actually see what the water ice looked like. Cool. And the water ice actually kind of looked like it had craters on it. It wasn't this pristine glacier sitting on the surface. Yeah. It just kind of looked like a higher albedo, brighter surface of the crater floor. So this kind of matches. And those were looking at these large deposits in craters that were thought to be stable over time. But this idea that, you know, oh, these deposits look old, but the tiny craters say they must be young. We're saying that they don't have to be young. And this is kind of some more supporting evidence for that. And then just kind of the final slide one, it's the F we can talk about. So it has a very confusing title. It's lowest maximum temperature. So in the maximum temperature plots of A and B, that's the maximum temperature of any pixel in the crater region. But there's all these different pixels. So what if one of those pixels is actually really cold? So it's saying here, we're saying because, you know, you have maybe 10 pixels in this region of permanent darkness, maybe the one in the center is colder than the one out here. So we're showing, okay, maybe it's even possible there could be some water ice at the surface.
I'm with you.
Pretty much what it's saying is like, we can't use these as a constraint. So that's actually kind of the paper's benefited from the fact we didn't get around publishing it right away. So because we've had this whole additional data set that's been added to it that really, I think, kind of adds to the story. And I think if we want to go back to, I think, figure 6 and 7, we can talk about the other little story I mentioned. Was it just 7? It might be just 7. Okay. Oh, yes. Just 7.
Just 7, yeah.
My brain, which like what figures were panels, which figures weren't. So I mentioned there was that longitudinal variation. So what this is kind of, there's kind of 2 stories being told here, and I'll talk about them first. I'll break them into 2 different things. So the first one is this longitudinal variation. So previously I showed that there was this huge increase in depth diameters with huge increase in percentage of craters that had water ice with longitude in a certain region. So there's this area that has a lot of water ice, rest of the surface doesn't really. Then that kind of ties into the story of how thick are these water ice deposits. Ooh. Now, there's been a lot of work on this because you want to know the volume. Right. And we have area from radar, but we don't have thickness. Right. And one of the proposed methods actually has been looking at depth diameters relationship. So here, what I've really done is I've just plotted the depth diameters of the radar bright and the non-radar bright, and to see if they're different, to see if we can actually measure the amount of radar bright material in these craters. Okay. And some of them, the radar bright craters are shallower, sometimes they're deeper. It's kind of hard. There's a better plot showing it, but I think the main thing here is you can see there's large error bars. Oh yeah. Yeah, I mean, that's when I talk about, I was like, so, and previous studies have pointed that the thickness of the radar bright deposits are on the order of tens, maximum like 100 meters. That's the error bar of these measurements. But that's really kind of what this is showing. There's kind of, that's the same question. Whenever you do depth diameters of craters that have ice in it, people are like, oh, can we measure the thickness of the ice? And you're just like, the data is too messy. I'm really sorry.
Bummer.
But so that's really what this figure is talking about. And I think if I go down, I think it might actually be the last figure. Sorry to bounce around. I said I was gonna do this linearly in my head. It's bouncing all around.
It's all great. Okay, got 9 and 10 on diameter, latitude, and then
yeah. So actually, if you just want to leave both of them up because they both are these tie into the two stories. So the story about can I use the craters to measure the depth diameter craters to measure the thickness of the ice? That's kind of figure 10.
There we go.
So what this is showing is, so I have the red and black are the measurements from the study. I took the error bars off this. There are massive error bars on this. It's just, you couldn't see the lines then. Right. But the lines are also the fits to it. So it's just like a simple linear fit. And the reason we're doing this is to show that, yes, if you do a linear fit to this data, and which is this Robonenkos data has done that, and they had a statistical argument saying you could see it. We were kind of a bit more on the side of it's really, really messy data. So even though we see that same linear trend to crater shallowing with getting closer to the pole, I think what I'm just trying to show here is that the data is too messy, and maybe it's real, but maybe it's not. Okay. So that's kind of the summary here. It's, there's a lot of exciting things we can do with this data set, but the simple fact is, the data, there's a mixture of both, we're measuring from spacecraft hundreds of kilometers off the surface, from another planet, and also just the fact that craters have natural variation, and trying to find tens of meters of difference on some sort of average is going to be tough. And so that's kind of where we're at with measuring. So there's other ways. There's a lot of really good work by actually Ariel, who's one of the other co-authors on here, trying to measure the thickness of Raider Bright deposit. There's been a lot of really exciting work by lots of people in doing that. So it's just, this may not be the best technique. I mean, it could also be, with more data, with other stuff. Right. But so I think the other story, just to kind of wrap up the many stories I've tangentially touched on, is figure 9, just to zoom up slightly. And this was this weird longitudinal difference. Yes. And so the obvious thing, if you know Mercury in polar regions, is that there's this massive crater called Prokofiev right in the middle of it. Okay. And Prokofiev is at this longitudinal region where you see this massive increase in number of craters that Raider Brights. So the question is, are these all actually secondary craters that are quite shallow? Because you expect them to be shallow. Right. And you're like, oh, when we said that, we're like, we've solved this problem. We're going to write this nice story. And then it's like, let's just double check that the secondary craters are actually substantially shallower. So what we did is we went and found the secondary craters that were like, I am sure this crater is a secondary crater of Prokofiev, not just this is a crater nearby Prokofiev. Right. This one, I can see the trail coming from it,
Yes, right.
I wouldn't, but let's see. So that's why there's only, I think there's one's double plotted. So I think there's 7 craters on here. But the thing, unfortunately, was that they're not all super shallow. So the story is the jury's still out. Right. And there's some discussion, it could be a hot pole, cold pole, because some poles of Mercury, longitudes of Mercury are colder and hotter. It doesn't line up exactly. It is one of those things we just probably don't know. And perhaps another thing with more data can help. I think some of the best data sources would have been Arecibo, but so it's just one of those things we don't understand. We thought we understood it. We thought we were going to wrap that all up nicely in the story, and we did not. So there's more work to be done. So I think that kind of is a nice way of ending, kind of talking about this, was that this is answered some questions. The study, it's told us that because there's Raider Bright water deposits in these small craters doesn't mean that the water ice got to Mercury yesterday. Right. It kind of leaves that question open, but it does mean that they are stable there. And the kind of cool thing is thinking about where to go in the future, because the Messenger mission is finished. Someone called it a litho-breaking experiment that was very successful into the surface. And so we're kind of, where are we going next? And the exciting thing is Bepi-Colombo, which is launched and it's on its way. And Bepi-Colombo is really exciting because it has a very different orbit.
Okay.
Has a similar suite of instruments, including an altimeter.
Nice.
But it's actually going to measure North and South Pole.
Okay.
So everyone who studied, like especially topography of these polar regions, everything's in the North Pole. I've only looked at the North Pole. I actually don't even know what the South Pole craters are really called because I don't work on it. And suddenly we're going to have data sets for the North and South Pole.
So is the anticipated altitude of that instrument smaller?
Yeah, so I can't remember the exact orbit, but it's going to be coming. It's going to be closer for more of the surface. So Mercury, the closest pass was almost always at about 82.
Yeah. Okay.
So we have incredibly good coverage at 82. But the Bepi-Colombo is going to get coverage pretty much all the way across the surface, which there's just not just polar science. There's going to be so much science to be done there. Right. But all these things, you can the biggest thing is we can repeat the same studies in the South with better data and redo the studies in the North with better data, and the data was comparable North and South. So it's really kind of like a ripe, exciting thing. Sometimes it kind of feels like these studies are just the trials for Bepi. Oh yeah. Like, oh yeah, let me show you, let me try out this technique and see if it works. And then we can decide if it works for Bepi. So I think that's what makes Mercury science quite fun, because, you hope a lot of things might get answered. There's going to be more questions, but you're like, oh, maybe in a couple of years we'll know these things better.
So one of the other points that you hit several times as you were going through, and it might partially be related to the altitude, was just the resolution available of the data. And so is the new mission going to be an order of magnitude better resolution?
Yeah, it's not, I want to say an order of magnitude, but at areas it's going to double. So the biggest issue with working on Mercury data is the variation. And you don't get the same quality resolution across the surface. And it actually makes science really difficult, because how do you compare 82 degrees to 65 degrees if the resolution is different?
Okay.
And the big thing about Bepi is it's going to have a very uniform resolution. So it's going to make science, it's going to reduce a lot of the grief in my PhD, which was working with these varying resolutions. It's like, oh, I did all of that work, and that someone's going to get a data set that's so much easier to work with. This is so unfair. I'll find the person at the conference. I'll be like, it's so unfair. This isn't right.
Well, pioneering study. It shall always be cited as the pioneering study. And,
Yeah. So, I mean, Mercury resolution is never going to be Martian resolution or lunar resolution. It's just simple fact of the environment. It's a really tough environment for spacecraft to operate in. Yep. And so that's just, I mean, kind of those things you're happy you have data.
Sometimes, yes. some even variable is better than none.
Yeah. And it's a fun thing to work on. I always feel like it's a planet that gets overlooked. Often you see it in textbooks just like bunched with the moon, like as a little side, and I'm like, it's such a good planet.
Oh, very cool. Very cool. Hannah, I want to thank you so much for walking through your really lovely article, a thought-provoking article on Mercury. So thank you.
Thank you.
All right. And that'll do for this one, everyone. And I hope it made your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.